So to introduce discrete time Markov chains, let us step out of the Bayesian context for the moment. And let's discuss DTMC, which is discrete time Markov chains in general. A stochastic process is a sequence of random variables indexed by time. And this stochastic process can be denoted by xt. So that represents x0, x1, x2, x3, etc. So the sequence indicated indexed by time. So in our discussion, we're interested in discrete time points. So t will take values in the natural numbers, 0, 1, 2, 3, etc. A stochastic process is called a Markov chain if it satisfies this particular property. Here, the probability of xt plus 1, that is the x value at the t plus 1 time point, given all the previous time points x's, x0 all the way up to xt, is equal to the probability of xt plus 1 given xt alone. This is known as the Markovian assumption, where conditioning on the present xt, what happens at the next time point xt plus 1 is independent of the past. The past is everything before the present. So time 0 all the way up to time t minus 1. Let's introduce a few key components of a discrete time Markov chain. The first thing is its state space. The state space of a discrete time Markov chain S is the set of values that xt's can take on. In most of our applications, the state space will be continuous. However, for simplicity, let's illustrate the idea of Markov chains here with discrete state space. That is the case where each of the xt's at each time point takes values between 1 and j, where this is either a finite set, which we will illustrate here, or a countably infinite set. The other component of a Markov chain is the initial distribution, and that is the distribution of x0. For discrete state space Markov chains, the initial distribution can be summarized as a j-dimensional vector lambda, where the jth entry of lambda is the probability that x0 is equal to j. And that's, say, what is the distribution of x at the very first time point. The last thing is a transition probability, and that is the conditional distribution of xt plus 1 given xt. So that is this probability over here. For discrete state space Markov chains, this transition probability can be summarized as a j by j transition matrix P, where the ijth entry of P is the probability that we will end up in state j at the next time point, x plus 1, given that currently at time t, we are in state I. In other words, given the current state I, Pij is the probability that the next state is j. You can imagine that for the transition matrix, each row will sum up to 1. So for a discrete state space DTMC with initial distribution lambda and transition matrix P, it has some properties. So first of all, lambda times P, which is a j-dimensional vector times the j by j matrix, is also going to be a length j vector. And it turns out it's quite easy to show that actually. This vector, lambda times P, is also a stochastic vector. So the entries are going to sum up to 1, and all of them are going to be greater than or equal to 0. And the jth entry of this vector is the probability that x1 is equal to j. Recall that lambda gives us the probability that x0 is equal to one of each of the j's. More generally, probability that xt at the tth time point is equal to j is given by the jth entry of lambda times p raised to the tth power. In addition, for t and n, which are greater than 0 and integers, p raised to the nth power, so the transition matrix raised to the nth power, is also going to be a transition matrix, and that is the transition matrix after n steps. The ijth entry of p raised to the nth power is the probability that we get to state j in n steps, given that currently we are in state I. This Pn matrix allows us to obtain the probability to go from one state to another in n time points. It also allows us to find out the expected time it takes to go from one state to another. For continuous state space Markov chains, we cannot describe everything inside a matrix and use simple matrix product to figure out the transition probabilities. However, we can still figure out what is the conditional density and what is the expected time to go from one value to another. Let's introduce some last bunch of definitions. A Markov chain is called irreducible if for all ij's in the state space, so ij's between 1 and large j, there's a non-zero probability of transitioning from state I to state j in finite time. So given any two states, I can go from one state to another. A state I is called recurrent if the chain will eventually return to state I with probability 1. Otherwise, it is called transient. If the expected time to return to state I is finite, then state I is called positive recurrent. The period of a state I is the greatest common divisor of n's, which satisfy pii raised to the nth power is greater than 0. In other words, the probability of returning to state I from state I in n steps is non-zero. If all of the states have period 1, then the Markov chain is called aperiodic. And if a Markov chain is irreducible and aperiodic, it is said to be ergodic. So that is a lot of definitions. And usually if you take a class on stochastic processes, it goes over all of these definitions and properties of Markov chains for you. You might wonder, why do we care about the ergodicity of a Markov chain? Well, this is related actually to the stationary distribution of a Markov chain and something called the ergodic theorem. But before that, let me illustrate a few examples of Markov chains. So here are 3 examples summarized in 3 graphs and corresponding transition matrices. The first example, so for each of the examples, there are 3 possible states. So the state space contains 1, 2, and 3. At each time point, x takes values in 1, 2, or 3. The arrows between the states describes the transition probability from one state to another. For example, given that you're currently in state 1, there is 40% chance you will go to state 2 in the next time point. There is 20% chance you will stay in state 1, and there's 40% of chance that you go into state 3. The first example here is a Markov chain that is not irreducible. In this particular example, you can see that 1 can go to 2, 2 can go to 1, 1 can go to 3, but once you get into 3, you are stuck. Because once you get into 3, then you have a 100% probability to stay inside 3 at the next time point. In this case, the state 3 is called an absorbing state. So this doesn't satisfy the irreducibility requirement because we cannot go from state 3 to state 1. The second example is one where the Markov chain is irreducible. So you can get from any of the 3 states to another of the 3 states. You can go from 1 to 2, you can go from 1 to 3, you can go from 2 to 1 like this, etc. However, it is periodic. You can see that once you're in 1, then at the next time point you are definitely going to 2. And then at the next time point you are definitely going to 3, and then at the next time point you will cycle back to 1. So this Markov chain is periodic. The last example is one where the Markov chain is irreducible and aperiodic. In other words, it is ergodic. You can see that you can get from one state to another. And at the same time, the period of each of the states is actually equal to 1. So why do we care about ergodicity? This is because when a Markov chain is ergodic, then a unique stationary distribution exists. Suppose that the probability of being in state J does not depend on the initial states after a very large number of steps. Specifically, suppose that for each state J, there is a probability pi j such that pi j is equal to the limit of Pn's ijth entry as n goes to infinity. And this pi j, which is the ijth entry of the Pn matrix, is independent of the value I. So what is this saying? This is saying that essentially you can see that P raised to the nth power is the transition matrix after n steps. And that's ijth entry is the probability that I will end up in the jth state after n steps, conditioning on I started in state I. If this thing is independent of I, it tells us that no matter where we started, we will end up in the same distribution. The probability that we end up in state J will not change depending on where we started at the beginning. Then the distribution of pi, so this should be a vector pi, sorry, a bold pi. The vector pi, which has a total of j entries, the jth entry called pi j, is called the stationary distribution of the Markov chain. In other words, that's what our x converges to as the time points gets larger and larger. If a Markov chain is ergodic, then there exists a unique stationary distribution for the Markov chain. If it is not ergodic, then this is not guaranteed. Let's see an example. And this example concerns DNA mutations. So let's consider a Markov chain of mutations of DNA. By the way, this example is from Rizzo book, example 2.7. So a Markov chain for mutations of DNA. A DNA nucleotide has 4 possible states. So A, T, G, C are the 4 possible states. We can denote them by 1, 2, 3, 4. For each point of time, the model state changes with probability 3 alpha equally spread over the 3 other states. In other words, the transition matrix P is given by this matrix here, where on the diagonals, the probability of staying in the current state is 1 minus 3 alpha, and the alpha diagonals are all alphas, because there's 3 alpha that's split between the 3 states. Let's consider the case where alpha is equal to 0.1. Then P is the matrix where it has 0.7 on the diagonals and 0.1 on the off-diagonal entries. Oops. Let's try to figure out what is what is p raised to the second power? So what's the two-step transition matrix? What's the three-step transition matrix? And C, what is the probability of ending in state J given initial state I? So let's first store the P matrix inside R. So it's a matrix of 0.1s except on the diagonals, which are equal to 0.7. And let's raise this transition matrix to different powers and see what happens. When we raise P to the second power, we can see that P squared is equal to this matrix here. As an example, if you started in state 1, then there is a 52% probability you will stay in state 1 after 2 steps. There's a 16% probability you will go into state 2 in 2 steps, etc. And this one below is P raised to the third power. For example, if you started in state 2, then there is 19.6% probability you will end up in state 1 in 3 steps. And now let's raise P to a really large power, say 10th power. You can even do it for higher. And we will do this by using the EXPM package inside R instead of doing the multiplication of 10 P's. So this is the syntax for P raised to the 10th power. And this is what we get. You can see that this time, wherever you started, say you started from state 1, then you have about 25% of chance ending up in each of the possible states. So if you started in state 3, things are quite similar, where the chance of ending up in states 1 to 4 is all close to 0.25. So this might enable you to guess the stationary distribution for this particular Markov chain. And that is the stationary distribution pi is the vector 0.25, 0.25, 0.25, 0.25. In other words, when you run the Markov chain long enough, then there is 1/4 probability ending up in each state. So there's another way we can figure out what is the stationary distribution for discrete state space Markov chains. And that's by doing eigenvalue decomposition, eigendecomposition of the P matrix. If you do eigen of P, then it returns you the eigenvalues and the eigenvectors. So this is the first eigenvector corresponding to eigenvalue of 1. This is the second eigenvector corresponding to eigenvalue of 0.6, etc. So we can see that the first column, if we normalize it so that the sum of the entries is equal to 1, then the first eigenvector becomes 0.25, 0.25, 0.25, 0.25, which is our stationary distribution. And why is that the case? This is because, as you can see, the invariance or the stationary distribution needs to satisfy pi times p equals pi. So once we get into the stationary distribution, when we transition again, we will stay inside the stationary distribution. And because of this, the pi vector is going to be the left eigenvector of p with corresponding eigenvalue of 1. Okay, so that was a quick crash course of Markov chains. Let's go back to MCMC and see how is all of these related to Bayesian inference. So why do we care about Markov chains and all of those transitions on eigenvectors when we're interested in estimating what is the posterior distribution of theta? Well, let's recall that what we want to do is to draw samples from the posterior distribution. So we can use Monte Carlo methods to get the posterior expectation of g theta. However, we were not able to, a lot of the times, sample directly from the posterior distribution. The idea of MCMC is that we want to construct a Markov chain, theta t, where the stationary distribution is the posterior distribution, f theta given x. If the Markov chain theta t is ergodic, then theta t will converge to the posterior distribution. In other words, if we draw theta t conditioning on theta t minus 1 a large number of times, eventually the theta t draws that we obtain will approximate the posterior distribution of theta. The question is, how do we set up the Markov chain? In the next few weeks, we will introduce some possible methods. Specifically, we will introduce the Metropolis Hastings and the Gibbs sampling algorithms for MCMC.